talked about flow rates and concentration and mass mole and volume fraction and all these little kind of basic skills that'll make it possible to actually perform mass balances or material balances. And so now we've kind of moved on to lecture 4, and which are the fundamentals of material balances. And so I'm going to kind of talk about kind of two main things today, and kind of look at other kind of peripheral aspects related to the material balance process. And so we're going to define the processes, which is kind of important, and then we're going to look at strategies for solving material balance problems. And this kind of becomes a little more profound and useful, especially when you get into more thermodynamic type of calculations, kind of understanding the concept of the system boundary. And so in this instance, processes are defined by the relationship between mass and the system boundary. So mass flowing in and out of the system boundary. When we start talking about energy balances, we talk about energy crossing system boundaries, and we only talk about the first law of thermodynamics in this class, but later classes, namely thermodynamics, you talk about additional laws of thermodynamics. But the system boundary is very, very important, particularly for energy, because of the way energy can cross system boundaries in the different forms, and we'll get to that when we talk about energy balances. In this instance, processes are defined by the relationship between mass and the system boundary. I kind of just said that. I was kind of trying to put together some examples to make it a little more interesting than this kind of blank white background on my PowerPoint slide here. But for a batch process, no mass exits the system during the process. And the example I've always kind of used in class has been metal stamping, but I have a video of metal stamping, and so it's not quite that straightforward. So there's some little bending of the definitions, bending of the rules, so to speak. And so I'll kind of show this video, and then let me fix the pointer here so I can actually use it as a pointer. And let's see, there we go. So I don't know if we'll watch the whole Society of Manufacturing Engineers video. But
multiple operations may be carried out on sheet metal stock either at a single die station or at multiple stations within a single stroke of the press.
Let me pause it. I'm pretty sure you can hear what the narrator's saying. The one thing I want to kind of point out is look for losses of mass in this process, because before I had said that a batch process, there's no mass loss. But if you kind of look...
dies used in single-station operations can be either compound dies or combination dies. Compound dies are press tools in which only cutting operations are done, usually blanking and hole punching. Combination dies are press tools in which a cutting operation, usually blanking, is combined.
So if you look, they're punching out basically a paint tray from this kind of stock of metal, but there's some leftover, right? So technically with a batch process, there isn't supposed to be any mass loss. And another example people tend to use for batch processing is like a toaster, even though you do kind of bake off some moisture, so there's a little bit of mass loss. So based on that, batch processing is a little bit hard to define, but ideally no mass exits the system during the process. For this next process we're going to talk about is a continuous process. and mass flows into and out of the system at the same time. And then if you don't know what I do a lot of polymer extrusion in terms of research. And then I didn't realize that this video didn't have half of the system. And so this is a polymer extrusion system. You can use it to make blends that you can actually chop it up. I tend to make filaments because we make stuff for 3D printers most of the time. Let me get back to the laser pointer. I'm sorry. So material typically flows in here, gets melted down, and it comes out. And it's pretty much a continuous process. I mean, if you continually fed the material to this machine, it would kind of just go on. And I kind of have a video here, and so it's being water cooled, but the filament's coming out, and then we're winding it. And we're actually making a 3D printer filament. And in this instance, we actually weren't making a 3D printer filament. We were drawing it really, really thin, so we can actually get to a diameter that's equivalent to like a thread to make like polyester clothing. And what we were doing here is we're making a really, really thin filament for water filtration. So we don't have to just make filaments for 3D printing. We also have an apparati that chops it up, so we can go to an injection molder. An injection molding operation is kind of an example of a batch process as well. There's very little mass loss in injection molding. So we have a batch process. I think a toaster may be a better example than the metal stamping. As you see, there is quite a bit of mass loss, but typically you're not losing mass during a batch process. Continuous process, it's going on, so mass is flowing into and out of the system at the same time. Maybe didn't really explain that well. We're putting in plastic pellets into this side. It comes out in a molten state that we're winding up into a filament. So there's a change in form, but ideally there's not any mass loss. The last one I have is a semi-batch, so it's neither a batch nor continuous. And so the example I always like to use is evaporating boiling water on a stove. There's definitely mass loss there. In fact, you can boil off water and end up with an empty pot. And then I actually went and found a video of somebody boiling water, and it's funny. But how to boil water, I guess it's British. Don't want to spell it. That's an awesome stove. Atomic symbol. But, I think it's funny that somebody went to the trouble to make a video. So, found this humorous actually. Oh, it's happening. Alright, so we got the water boiling. Convert it from liquid to vapor. So there's definitely a mass loss. It's a nice Italian company there. So anyway, that's a semi-batch. It's neither a batch nor continuous. We're not continually flowing material into the boiling water, or sorry, into the pot to boil it off. And but there is a mass loss, a definite mass loss. The batch process of the metal stamping, there's a little bit of mass loss, but ideally you don't have mass loss in the batch process. So kind of three examples of processing, and kind of keep that in mind. And hopefully, and Coke cans are actually made with the stamping process too. But anyway, when particularly for this class, and if you ever get into a situation in the future where you're working on a job and you're in something that makes something, a factory or something. Right? I used to work in the semiconductor industry. I worked in semiconductor factories. Kind of think about the different types of processes in the place you work at, that kind of thing. And it kind of helps to put things in the context of mass going in, mass going out kind of thing. And we will have some semiconductor processing problems later on in this class, as well as metals refining process problems, that kind of deal in these kind of contexts. So in a continuous process, a batch process, yada yada yada, that kind of thing. So hopefully these videos are a little informative. Time comes into the picture. And so steady state processes, the process doesn't change with time. And for the most part, the problems we'll do in this class are steady state. Transient, unsteady state. So unsteady state, the process does change with time. And I feel like I was supposed to have some animations here. But anyway, steady state process does not change with time. Differential balances. So if you have an unsteady state process, you can take a snapshot and do a balance at one point in time. Steady state, since it doesn't change with time, you don't really need to worry about treating things in terms of a differential balance. But if it's steady state, okay, you can use integral balances. So balances over a period of time. So words like how long it will take, if you're reading a problem in this class and it says how long will it take to make 2 pounds of lettuce or something, that's a characteristic of an integral balance. So kind of the general balance equation, and we talked about it I think in lecture 1. Input equals output, basically. And so input equals output, or mass in equals mass out. And that's the simplest general balance equation. And the book uses an example of a city population. So population changing over time, people moving away, babies being born, that kind of thing. People moving to the city changes the population, right? So input plus generation minus output minus consumption equals accumulation. And I'm not really going in a linear order, I apologize. But when we set up these problems, okay, and this is on page 85, and it's funny, I just realized that their citation has a spelling error, and it's coming out right at me now. But anyway, input equals generation minus output minus consumption equals accumulation is kind of the more complex way. And in most instances, input equals output. Conservation of mass, okay, as the kind of the guiding principle of mass balance problems. And so mass can either be created or destroyed. And so if you're balancing total mass, generation and consumption equals 0. If no chemical reactions occur, and chemical reactions will occur later. But for these early problems, we're talking about non-reactive material balances. If no chemical reactions occur, generation and consumption equals 0. And if you're working with a steady state system, accumulation always will equal 0. So we're not accumulating. And if the numbers don't work out right, then there's some accumulation. So that's kind of an example of identifying loss to your system. So if generation equals 0 and consumption equals 0 and accumulation equals 0, mathematically input equals output. And so that's basically how you get to input equals output from this. I'm pointing at it with my hand. You can't see it. I apologize. That's how you get to input versus output from this a little bit more complex equation. All right, so mass balance is explained by this guy who makes whiskey. And I was told that this was actually a show, so I better be careful with copyrighted materials for some moonshine guy. I don't watch much TV. But distillation, okay, distilling, and you don't have to just distill alcohol, basically. You can use distilling in a metal refining process. And we'll see an example later in this class of zinc and cadmium, I believe are the two metals that you can separate by distillation. But distilling water and alcohol, and it doesn't have to be a whiskey guy. Alcohol is used in industrial uses as well. So we have a mixture of 90% water and 10% alcohol, and it's coming into a still. We're not doing energy balance problems right now, so we're not really worried about how much heat's being added to the system. But we have this, and hopefully you realize that this is mass flow rate. It's M with a dot, and we have two output streams, okay? And so it's 60% water and 40% alcohol, and the bottom stream is 100% water. And so the question they're asking now is how fast the two mixtures exit the still. And I'm going to show it to you two ways. So we're gonna work it out right now, and then we'll see like an animated PowerPoint version of the solution. All right, here's kind of a text version of the distillery problem that we are going to work out now. And I'll go ahead and read it to you. You can read along as well. The way it's written is pretty similar to how most of the problems will be written in this class. And let's go ahead and read it. So in a distillery, a mixture of 90% water and 10% alcohol, and it's very important to specify what the designation is. It could either be by mass, it could either be by mole, or it could either be by volume. So those are the three combinations we work with in this class. And so I specified here it's by mass. If it was by mole or by volume, we'd have to know some other things. So we'd have to know what kind of alcohol it was. So if it was ethanol, we would know the chemical formula of ethanol, that kind of thing. But we don't need to worry about that right now because we know it's by mass. And so they flow into a still. Okay, so this mixture is flowing to a still at 100 kilograms per hour. So we have two exit streams, as we saw on our little cartoon on the previous slide, and they emerge from the still. Okay, so one, a stream composed of 60% water and 40% alcohol, and two, a stream composed of 100% water. And the key question here is, what are the two mass flow rates of the exit streams? And so the first thing it helps to do is kind of go and highlight the kind of important bits of information. And so a mixture, so I put by mass, I highlighted by mass, but we also have a composition. So it's 90% water, and 10% alcohol. We also have an incoming mass flow rate, so that's 100 kilograms per hour. And then we have two exit streams emerging, and the information we have here is composition information. And I'm going to go ahead and assume by mass because I don't know otherwise. It's not otherwise specified. And the internal flow rate was specified by mass, so it's a good assumption to say this is by mass, even though I didn't specify. And I'm usually a little better at specifying in the problems. So we're going to assume this is by mass. And we have a composition. So stream one, we know it's 40%. So it's 60% water and 40% alcohol. And we know that the bottom stream is 100% water. All right. Always, always, always draw a flow chart. And some of you may be taking statics or mechanics materials or whatever it's called now. I think it's a combination statics, mechanics, materials. And the key to solving most statics and mechanics materials problems is the free body diagram. For this class, the flow chart is the analogy to the free body diagram. And flow charts don't have to be too confusing or too elegant. You can typically use a little box to identify your system. And so this is the still. And if I had heat or something and I was doing an energy balance problem, I may indicate, on the chart where the heater is or that kind of thing. So we know our input stream And I'm going to, I think later on I designated as something different, but I'm just going to call it, I'm just going to call it M naught here. And I know some things, so it helps to list things. So we know it's a mass flow rate, it's M naught. The flow rate is 100 kilograms per hour. And I'm going to go ahead and abbreviate water as a W and abbreviate alcohol with an A. So it's 90% water and 10% alcohol. And then it said we had two streams. And so we had an upper stream that was 60% water and 40% alcohol. And then we had a bottom stream that was 100% water. Okay, so now we have, and it may help to also specify that this is by mass. And by mass. And it almost doesn't matter because it's 100%, but we'll also specify by mass. And I don't always do this, but it helps actually. Again, I'll say it before and I'll say it again. I've said it before and I'll say it again. This class, the key to this class is bookkeeping. Really, it really is, and writing everything down. So the way we do this now is we're going to assume we can go back and look at our general balance equation, right? And so we said input plus generation minus output minus consumption equals accumulation. Okay, and we can assume it's a steady state. We have a flow rate. It doesn't really say for how long it's flowing. It just wants to know what the two mass flow rates of the exit streams are. And so we're assuming steady state. There's no chemical reactions. There's no, okay, so we're working with a steady state. There's no chemical reactions. And we pretty much, we pretty much want to solve for the total mass. So balance the total mass. So there's no accumulation, there's no consumption, there's no generation. Okay, so input equals output. And so now we can set up some equations based on input versus output. Okay, and there's two species, right? So we have two species, and so we generally count or call the things that are coming in and coming out species. So we have two species. And water and alcohol. Alcohol, if I spelled it right. So we're going to set up two balance equations based on input equals output. Oops. Input equals output. So the first balance we're going to do is a water balance. And so where do we see water? Oh, another thing I neglected to do, we want to label the process streams. Okay, and it's very, very important. And I'll write it in red. Okay, in this case I called it M naught, and sometimes I change the numbers, like sometimes I call this one M1, M2, M3, that kind of thing. So don't get too bogged down with the convention. Just make sure you label the balances. I'm sorry, the process streams. So for the water balance, 90% translates to 0.9. And we have water in M1 and we have water in M2. Okay. And the percentage of water in M1, did I get the percentages right? Yeah, 60% water. Okay. Oops, and I called this M naught. Excuse me. So 0.9 M naught equals 0.6 M1 plus, we have water here, and it's 1. And if you look, its input equals output. Didn't mean to make output 2 words. So we have that equation. So we have another equation. And I spelled it kind of poorly. Let me fix it for you all. And again, we have M naught, so it's 0.1. And we only have alcohol in M naught, sorry, 0.1 M naught. We only have alcohol in this stream we've labeled M1. And it's 0.4. For M1. Did a bad job. Oh man, hold on. Don't judge me too harshly. All right, so there's some knowns and some unknowns. M naught is known. And that's 100 kilograms per hour. Okay, so M naught is known, it's 100 kilograms per hour. And we are trying to solve for M1 and M2. So mass flow rate 1 and mass flow rate 2. That's what the question's asking. So we can rewrite this. And so 0.9 times 100 is 90, and remember the units, but we can put the units in later. And this is 10. So 0.1 times 100 is 10. And so what do we have? We have 2 unknowns. And we have 2 equations. So we're ready to solve. And we can do some substitution. This one is the easiest to solve for. So we can solve for M1 first, okay? And so 10 divided by 0.4, I believe is 25. 25, so sure enough, it was 25. So from the alcohol balance, oops, excuse me. See, I got a little better at putting 0.4. I'm just rearranging it. And then we can plug that into this equation. And so you can just plug it back in to this one. And so now we have 90, and let me write out what we're doing just for completion. If it'll let me switch pens, there you go. So we can plug that into the water balance. And so 90 equals 0.6 times 25 plus M2. And so we can solve it this way. And I'll show you another balance that we tend to use to solve the equation. So M2 equals 75 per hour. So there's a third equation, and I tend to tell people or tell students to save it to kind of check your answer, but that's the total balance. And the total balance is also input equals output, and it's M naught equals M1 plus M2. And if you remember, M naught was 100 kilograms per hour. And we said that it's always good to circle your answer or highlight it some way. We said that M1 was 25. And M2 is 75. And so 25 plus 75 by my math does indeed equal 100. And so there you have it. We've done a simple mass balance problem. We solved for the two exit streams, M1 and M2. And we used the total balance equation to basically check our answer. You could also use the total balance equation to solve your problem as well. But I tend to advise people to use it to check their answer. So you can have another way to check it. But if you're in a time crunch situation like a test or something, it may be better to go the faster approach, because it would have been a little faster to solve with the total balance. So once you had M1, you could have easily used this total balance equation to solve for M2. But anyway, that's how you solve this distillery problem. All right, so you saw this problem worked out kind of the long way. So we made two equations, and I kind of have the more detailed solvency, I guess, or solution for this problem that we just saw. But it's a simple system of linear equations. It's actually really, really easy to solve, and substitution is the most direct and obvious way. And so basically we solved for M1, this one, and then plugged it in to this to the water balance equation. There was also the total balance equation, and we could have used that as well. But again, I always tell people to use the total balance equation to kind of check your answer. And so we solved it. We got M1 equals 25 kilograms per hour, M2 equals 75 kilograms per hour. That equals our input mass flow rate, which was 100 kilograms per hour. You could also use Kramer's rule, and so it's used to solve a system of equations. I tend to not use this for this class. I usually just use good old-fashioned algebra, but I kind of wanted to throw this out here and kind of show you. And so you have two systems. You could, and if you have three systems of equations, you make the matrix bigger. And so you solve for x and y basically, and x equals this matrix, so it's the solution of this matrix divided by the solution of this matrix, and y is the solution of this matrix divided by this matrix, and the variables come from these two equations. And if you remember, it's kind of a cross multiply, so it's basically by determinant, and so m times d minus b times n, and anyway, this is the equation we got, and this is the matrix we would have set up, and then you get the same answer. I think it's easier to use algebra, to be honest with you, and I almost think it's easier to do algebra even if we have three systems of equations, or a system of three equations, excuse me. But anyway, it's up to you, and you can also use like Gauss-Jordan elimination, that kind of thing as well. And some people tend to use like the solver on their calculator, and I think I can do it with this as well. But anyway, different ways, more than one way to skin a cat, as I've been told, and it's pretty much just algebra. So tips for success. So I said this in the solution: label all the process flow streams, and this is actually for the next question. We want to know the molar flow rate, so I got this slide a little bit out of order. In this problem, we wanted to know the mass flow rate. Okay, this next one we're going to look at, we want to know the molar flow rate, and it's a little bit more complicated because there's different nomenclatures, but we'll work through it, and it'll be pretty cool. You always want to analyze. You want to know what you want to know, or what you know, and what information is important for what you're trying to solve. So what do you know? So this one back here, we analyzed what we knew. So we knew the composition of the input streams and the two output streams. We knew the composition. It didn't really specify it here, but in the written version, we specified that the composition was given to us by mass, and we knew the incoming mass flow rate. So that was the information we knew. And we could use that information then to figure out the mass flow rates of the two exit streams using very simple algebra. Excuse me. So we're going to take a look at this problem next, and this one's right out of the Felder and Rousseau book as well. A gas stream, which is 18% by mole, hexane, and the balanced nitrogen, so it's a combustible gas and an inert gas mixed together, enters a condenser, and an exit stream leaves an exit gas stream leaves the condenser with all the nitrogen, okay, and the second stream of liquid hexane leaves at a rate of 1.5 liters per minute. And so it's not written that well, actually. But we have two questions. So what is the molar flow rate of the gas stream leaving the condenser? And what percentage of hexane is recovered as a liquid? Oh, this is a little bit of a harder one. Here would be, and here's what I was talking about. The language wasn't that great. So exit gas stream 5% by mole. And maybe I'm not doing him credit. Maybe when I rewrote it, I left out that it's 5% by mole hexane. Okay. But it has all the nitrogen with it. Okay, so all the nitrogen that went in is going out through this one. There's a little bit of hexane left. Okay, and so we want to know what the molar flow rate is of this gas stream, and then we want to know what percent of the hexane is recovered as a liquid. And to do that, first step in these problems, okay, we've analyzed it a little bit. It was a little confusing in the language. but then we make a process flow chart, and the process flow chart is always the key to solving these problems. It is our analogy of a free body diagram for this class anyway. And so here would be the process flow chart. So we have nitrogen. It's 18% by mole hexane, this input stream. How much percent by mole nitrogen is it? Well, 100 minus 18, and how much is that? 82%, if I can do math. So it's 82% nitrogen. This is 5% by mole hexane. So that means that 95% of this is nitrogen. And we have this in a different flow rate. So the only flow rate we actually have is this output in the liquid state. So we're going to have to do some conversions, which is exciting. Okay, so that's why we spent a lot of time doing unit conversion before we got into the nitty-gritty of material balancing. And so let's work through this one. It's a little bit more challenging than the distillery problem, but it's definitely worth our time to do. And so I'm going to work it out on the whiteboard. So we have our condenser, and I'm going to go ahead and kind of do my best to mimic the flow chart that we had on one of the previous slides. And so we had this stream coming in, and it was 82% nitrogen in the N2 form, and it was 18% hexane, which is C6H14, and then it had a liquid stream, and it was pure hexane. So all of this stream is hexane. Oops, what am I looking at? Excuse me. It was 1.50 liters per minute, and it's liquid. And that's what the problem specified. One thing that wasn't specified in my text version was the specific gravity of hexane, and that becomes a little bit important in solving this problem. So there's a lot of conversions, but let's finish doing this. And so they want to know the exit stream, the molar flow rate. So this is N2. So all the N2 is going here, so it's 95%. And it was C6, excuse me. Come on now. Tablet's acting strange today, but and it was 5%. And again, by mole, also by mole. And so the only flow rate we have is this 1.50 liters per minute. And so we have excuse me. The last one was mass, this one's mole. And I should probably label it a little more neatly. Neatness is also a big way, and not let me see, how do I want to do this? All right, well, let's label it another way. Sorry about that. We're going to go ahead and label this N1, and this is going to be N2, and we're going to label this N3, but we don't know it yet, so we're going to have to figure it out. So this time I decided just to do it 1, 2, and 3. Okay, and we want to know, what do we want to know? want to know what the molar flow rate of the exit gas stream is. So this is in gas, and this is also in gas. And so what they're doing here is they're purifying hexane, basically. So you had hexane mixed with nitrogen. You want to purify the hexane. And the distillery, we were purifying the alcohol, and there we were boiling off the alcohol, basically, and some water went with it. Here we were condensing out the hexane, so condensing, distilling. And so two things that these problems have in common is they're effectively separation problems. And so non-reactive material balances, for the most part, are separation problems. We're separating one element from a mixture, basically. Sometimes you're mixing two things together, so you're either putting something together or you're separating it. That's kind of a hidden concept of material balances. All right, so let's go ahead. So the only flow rate we have, and the key to solving this problem, is this one. And what the problem didn't really tell us in the language, and I honestly can't remember if it's my fault or if it's the book's fault. I should probably go look, but I'll just say it's the book's fault because I'm vain. The thing you have to do is that this is a volumetric flow rate. Okay, so this is V dot. And so we need to V dot to N dot. Okay. And so if you remember from converting this stuff, to go from volume to moles, you need to go to mass. Okay. So, and then to get, so, okay, so let me write this out so it's more sensical. So if we go to volume to mass, you need density. So remember that we talked about it in a past lecture. So volume to mass, you need density. Now we went molar, okay? You need the molecular mass. Molecular mass. And so I put mole mass, but molecular mass. You know, I should write it out just in case you're watching this without volume or something. Molecular mass. All right. So to go from volume to moles, you need to go to mass. So the I guess process step, oopsie. The process step is you got to go V to mass to moles, okay? And I'm putting flow rates, but it's the same if it's just straight up volume, mass, moles. So this is what you need to do. So we have a volumetric flow rate, 1.50 liters per minute, and we wanted to make it a molar flow rate. And so here's the things we need to do. So to get to density, we're going to get to density with a specific gravity. So the specific gravity of C6 H14, that equals to 0.659. And if we use the book's notation, so let's figure out the density of C6H14. Since we want to get to molar flow rate, we can use the density of water. and just we don't have to use the kilogram version. We can use the centimeters grams second version. Alrighty, and it is 1 gram. So we want to get the density, which I kind of wrote twice, I'm sorry. Here we'll just say, what does it equal? So 0.659, and it's very simple, okay, but I'm writing this out long, even though I don't really need to, just for bookkeeping purposes, because it's always good to keep track of what you're doing. And it seems like a waste of time maybe, but it's always good. I can't speak enough to just writing everything out, even if you think you're overdoing it. And so hopefully you can read my writing, or else it's all useless. 0.659. Yeah, if you can't read when I'm writing, it's not very helpful, is it? So hopefully I wrote it well. 0.659 grams per centimeters cubed. Okay, and so C6H14, so the molecular mass of, and I abbreviated it here, its molecular mass is 86 grams per mole. All right, so to get N3, we're going to start off with our volumetric flow rate of C6H14, and it is 1.5 liters and well, we have liters and we need a cubic centimeter, right? Because we put our density of C6H14 in terms of cubic centimeters. So by my math, there is 1,000 cubic centimeters in 1 liter. So that's going to handle that. The density, there are 0.659 grams, and we can label it (14), and this, we could say this is liters of C6H14, just for the bookkeeping. And I should have squeezed it in here, but I didn't. But pay attention to units. Units cancel. Grams per centimeters cubed. And the last thing we need is grams of C6H14. So there's 86 grams 14 in 1 mole. And 1 mole of C6H14. All right, so I'm going to do some canceling of the units to see if we're going to get the units we want. So molar flow rate, okay, should be, in this case, mole per minute. That's our goal. Is moles per minute. So liters of C6H14 cancels, centimeters cube cancels, grams of C6H14 cancels, and so the units we have left over now, I'm going to highlight it, mole per minute, and that's what we want. So we can plug and chug with confidence, and I do this all the time. I forget the equal sign. I'm sorry. So let's go ahead and plug and chug. So 1.5. You can hear my calculator buttons times 1000 times 0.659 and divided by 86. And I got 11.49 moles per minute. All right, now we have a molar flow rate. And you saw with the distilling problem that we can solve for other flow rates. We could solve for all of the flow rates based on one flow rate, even though this time this is an output flow rate. And it's a little bit more complicated algebra, as you will see. But let's take a look at what species we have. Okay, so I did the whole conversion. I probably should have looked at what species we have first. I kind of did, but didn't really say I was doing it. The two species we have are nitrogen and C6H14. Those are the two balances we're going to work out. We're going to work with these variables N1, N2, and N3. So N1, N2, and N3. And it's getting a little big, but hopefully you can follow along with my, my whiteboard. So the first balance we can do is hexane. So let's do a hexane balance. And you can use any abbreviation you want. And in case you get lost, hexane is C6. I was writing it as hex because, you know, being cool, I guess. So again, we're assuming input equals output. So input, I guess I'll go through the whole thing. Input plus generation minus output minus consumption equals accumulation. So we're assuming in this condenser that everything's coming out. There's no chemical reactions. Again, this is a separation problem. We're not consuming anything. We're not generating anything. And so once again, we're not generating, we're not consuming, we're not accumulating. So input equals output. So all of our balances will be of this form, input equals output. So we're going to say we had N1, and N1 was 18% hexane. And I'm sorry, it lagged. There we go. So it was 0.1 N1. Oh, excuse me. I have it written also out here. N2, we had some hexane as well. And so 0.95, oops, sorry, 0.05 hexane. .05 N2, and it was all of N3. So all of N3 is hexane, and we converted it to a molar flow rate, so everything's going to work out fine. Plus N3. And I'm going to rewrite it with what we know N3 to be in a second. And I'll show you how awesome it actually works out. And I'm going to rewrite hex balance. And I'll write hexane. And then we have the other one, the other balance, excuse me, which is the N2 balance. And we said it was 0.82, and kind of be careful sometimes with the nomenclature. NN, you don't want to get it mixed up. there's no N2 in, excuse me, there was no N2, there was no nitrogen, I'm going to say nitrogen in this one, but there is nitrogen in this one, and it was 0.95. Oh, come on. There you go. Equals 0.95 N2. And there's none in N3. So we can rewrite this hexane balance problem and then N3 is 11.49. And I'm going to leave the units off. We'll plug them in later. The reason why I leave the units off is it makes the equations kind of messy, makes them a little bit bulky. And so we have two unknowns. Two unknowns, and which are N1 and N2, and two equations. So we have our two equations, and so now we're going to have to solve it as a system of equations. And I tend to use elimination substitution when I do this. And so we can do 0.82 N1 equals 0.95 N2, and we can say 0.18 N1 equals 0.5 N2 plus 11.49, and what did I do? I think I multiplied everything by something. I multiplied, and so there's different ways to do it. And again, what I'm going to do is I want to get rid of one of the variables. And to get rid of one of the variables, I think I did this. Hold on. Oops. Oh, it's 0.05. I'm a dolt. I messed up the equation. See, I had it here and I left it off. So, my bad. Always orders of magnitude, big time. I'm leaving this mistake in. I won't edit it out because it's important. Okay, always check. So always. So I apologize for that error. Leaving it in the video, everyone makes mistakes, but always go back and check for them. And so I'm leaving it in. And so what I'm doing here is I want to get rid of a variable. And what I found I can do is, for this particular case, I can multiply both sides of this one by 19, and then multiply this one by -1. And so I'm going to rewrite it. So what I'm doing is I'm multiplying. So I'm multiplying -1, and I'm multiplying the bottom by 19, both sides, okay?
And so I'm going to rewrite it. And so I'm going to get negative 0.82 N1 equals negative 0.95 N2. And for this bottom one, I'm getting 3.42 N1, and that equals 0.95 N2 plus 217.93. And so I'm going to add them together. So if I add them together, I get a new equation. And so this new equation, negative 0.82, I'm just going to add them together. I get 2.6 equals, and this is going to go away. And so 217.93. So N1, so what I got? 83.1. And you can use it to check your answer, but this video has gotten kind of long, and so I'm going to use the total balance. So N1 equals N2 plus N3. And I can use it to solve it rather than plug it back in. Does it really save me a lot of time? It doesn't really. I'm gonna save this to check it, to check the answer. So 0. So we can just plug it back in. I can plug it into either one, right? 0.82 N1 equals 0.95 N2. And N1 times 83.1 equals 0.95 N2. So 71.73. And so it's a little messy. Let me fix that. Come on. Sorry. My computing woes. And again, moles per minute. So let's go back in our total balance. We'll use it to check. So right away, just kind of by general inspection, it looks okay because N1 is the biggest number, and it's going to be a sum of N2 and N3. N3 we know from our conversion was where did I get it? Yeah, 11.49. So we know N3 is 11.49. And so N1 equals N2 plus N3. And N1 was 83.1. It might be a little off, but it's not that far off. so let me just work it out. I can't do this in my head for whatever reason. Plus 11.49. So 83.22 if you add it up. So I'm off by a little bit, but not that much. So it's pretty close. It's pretty close. And yeah, this is acceptable. Okay, so I may have made some rounding differences and whatnot. So it's pretty close. So we worked it out. And what were we actually solving for? Well, we wanted to know what the molar flow rate of this one was, right? So we want to know that. So that's the big key. And we kind of had to solve for everything to get it. So into 71.73 is actually the answer. Oops. I don't know why I did that. Let me just do this. All right, so there you have it. That's how you solve it. We used molar flow rate, and we used a lot of concepts in that we've gone over already. So we definitely did unit conversion, and then we converted between the different flow rates. Oops, I got to the other problem we worked out. Excuse me. Definitely did unit conversion. We used specific gravity. And we converted from volume to mass to moles. So we've done quite a bit of the concepts leading up to this point in class to solve this problem. So hopefully things are kind of coming together in your brain. We solved it, and hopefully this was easy to follow. And anywho, this is what we got. So thank you. All right, so there was a part B, or a second question to this, and the fan on my tablet here is going crazy, so hopefully you can't hear it. So, oops, let me turn my pen on. Excuse me. So the part B, what percentage of hexane is recovered as a liquid? All right, so what percentage of hexane is recovered as a liquid? And so it's basically the recovery ratio is how we're going to solve it. And so the recovered this is the ratio over the input. This is supposed to be a C. So recovered over the input. And so if it lets me do it, I might have to do a reboot of this thing here pretty soon. So if you go back to the original problem, we had some input C6H14. And we had this as the recovered, so 1.5 liters per minute was recovered. We went through this whole hullabaloo to figure out the molar flow rate. So we can do things in terms of molar flow rates. And so this is actually the recovered. So the N3, the liquid hexane, is the recovered. And then the amount of hexane coming in was 18% of N1. So we can do things in terms of the molar flow rate. And so, excuse me. So recovery ratio will actually give us the percent recovered. And so the recovered C6H14 was basically N3 over the input was 0.18, which is what we kind of just said, N1. And so N3, if you remember, was 11.49 moles per minute, and 0.18 N1 was 83.81. I should probably make that more clear. So this is 0.18 N1, and if you work it out, you get 0.76, and they wanted it in a percent, so we'll just draw an arrow, 76%. And so that's how much, what percentage of hexane was recovered as a liquid.
All right, so we just saw the solution to this problem involving molar flow rate. Some key things you needed to solve this problem were the specific gravity of the hexane, and particularly the specific gravity of the liquid hexane, because that allowed us to calculate the molar flow rate of this stream. And we were then able to calculate the molar flow rate of your input, and then the one we wanted, which was the gas. And so when you have a molar flow rate, you're pretty much able to handle different states. That's kind of another concept of this problem that was kind of not really outright said, but it allows you, the molar flow rate allows you to basically perform the material balance on this problem. And oops, went the wrong way. So strategies, we've kind of gone over some strategies, or we'll kind of go over them again because they're kind of the key concepts, kind of my weekly takeaways, if you will. So setting up the equations is definitely the most important task, but how do you get there? And so the first thing you want to do is draw your flow chart. The flow chart, again, is the analogy to the free body diagram that you see in other classes. You need to write down the values, label the process streams, label all the variables at these known locations. That helps you set up your balances. For the most part in this class, it's input equals output. Assign algebraic symbols. So we were using N1, N2, N0, whatever for the molar flow rate. When we have volumetric flow rate, we use a V as in Victor. When we use mass flow rate, we typically use an M. You can use any variable you want, but just as long as you keep it straight. That's kind of the big thing. And pay attention if you have to convert between mass flow rate and molar flow rate or volumetric flow rate, like we did on this molar flow rate problem. We had to convert the volumetric flow rate to molar flow rate, and we actually converted it to mass flow rate on our way to molar flow rate. So anyway, if one can be written in terms of another, do so. So if you have, one of the flow rates is 2 times the other, or something like that, you can limit the amount of variables you have. So if you limit your variables, you limit the amount of equations you need. You base your units of the unknowns on the units of your knowns, right? So we know we needed to solve for an unknown molar flow rate, and it was kind of asked. Sometimes it's not outright asked, so if you don't know, if it's not asking directly for the unit, you can base it on the input units. So this one here, right, it asked for the molar flow rate, probably because there were 2 units involved here, 2 flow rates here. But if all of these were molar flow rates and it was never asked what what is the flow rate of this output stream? Let's see if I'm saying it in a way that makes sense. You could have assumed that it was asking for molar flow rate if all of these were already in molar flow rates. That's kind of what that means. So base the units of your unknowns on the units of your knowns. If you have a mixture of mass and mole flows, make them all the same depending on what you choose for a basis. And also, if you have a mixture of volumetric flows, I get hung up sometimes on mass and mole, but volumetric flow rate is also a big deal. Perform a degree of freedom analysis, and we kind of did when we worked out these problems, because I was pointing out we had two species and two unknowns kind of thing. So we had two unknowns and two equations, basically. So that's pretty much what a degree of freedom analysis is. And if solvable, solve your equations. Try to avoid simultaneous equations, but I think we're all capable of solving simultaneous equations. And so those are pretty much my weekly takeaways. Degree of freedom analysis, I said we're going to do a degree of freedom analysis, kind of an explanation. You need 0 degrees of freedom for your problem to be solvable. And so if your number of degrees of freedom equals 0, it's solvable. If your number of degrees of freedom is greater than 0, there's too many unknowns. Go back and check your degree of freedom analysis for a mistake, but don't even bother trying to solve it unless you get less than 0 degrees of freedom. If your degrees of freedom is like a negative number, less than 0, it's solvable, and you actually have too much information, so go back and check for mistakes again. And so the source of information to solve for the unknowns is pretty much our material balance. Okay, the physical information specified in the problem, so specific gravity, process specifications. So the exit flow rate is 2 times faster than the entering flow rate. So you could make an equation to solve for M2 just by saying M2 equals 2 times M1. I should have dots, I apologize. And then energy balances. Okay, we'll worry about energy balances later, probably after spring break. And then mole fractions. And we've already kind of seen this. Hopefully you've absorbed it by osmosis in some way, just by the way we've set up these problems and worked them out. If we have a kind of an example here, this has a stream of humid air. It's entering a condenser where 95% of the vapor of the air is condensed. The flow rate of the exit stream is 225 liters per hour, and the dry air is 21% by mole. Oxygen in the balance is nitrogen, so that means it's 79% nitrogen. So you want to calculate the flow rate of the gas leaving the condenser and the mole fractions of O2 and N2 in the water in this stream. And so this is just kind of a bunch of words, so it's easier to determine if you have a flow chart. If we look at this flow chart, we have 6 unknowns, really. So we have N1, N2, N3 here, N4, N5, N6. This is also out of the book, this example I'm doing. You have 3 material balances, so your 3 material balances are O2, N2, and H2O. You can solve for N3 here because you have a given volumetric flow rate. Okay, so back here, the flow rate of the exit stream is 225 liters per hour, so we could figure it out. Oh, well, it's also here, liters per hour. Anywho, there we go. You can solve it because of your volumetric flow rate. You know the relationship between N2 and N3, but you know the air is humid, but you don't know how much water, so you have to divide it up into 2 streams, right? So you had to divide this up into N1 and N2, and then you can't solve for N6. So this isn't solvable, basically. And so 6 unknowns minus 3 material balances, minus 1 because you have this volumetric flow rate, minus 1 because you know the relationship between N2 and N3. So 6 minus 3 minus 1 minus 1 equals 1. 1 degree of freedom, it's not solvable. Don't even bother to solve it. When you have situations where you have 2 species and you can make 2 equations, like we did on these first 2 examples, your degree of freedom is 0, so you know it's solvable. And I think I want to move on to solving problem with a volumetric flow rate because we haven't done that. So we've done a mass flow rate problem, we've done a molar flow rate problem. Let's go ahead and work a volumetric flow rate problem, and then you'll have some practice problems to work out, and we'll kind of take it from there.
All right, so here we have a problem dealing with volumetric flow rate. And we kind of dealt with volumetric flow rate in the previous problem because we had to convert that volumetric flow rate to a molar flow rate so we could solve for another molar flow rate. Here, we're dealing with total volumetric flow rate. So we have a volumetric flow rate coming in, and we have a volumetric flow rate coming out, and we're going to have to figure it out. And then we're going to look at composition of the product gas. And I off the bat, I kind of apologize. When I import text into this app, it doesn't give me subscripts or superscripts. And I swear I typed it out with subscripts and superscripts. So please bear with me. These are all gases, and this is 25% CO2, 4% O2, and 20% good old-fashioned H2O, and then 51% N2. And then this is cubic meters. So I'll go ahead and I'll read through the whole problem. And so it says a gas containing 25% CO2, 4% O2, 20% H2O, and 51% N2 by volume. So that's a key thing. So we're getting some information there. So we're getting a composition, and then we're getting by volume. So we're getting how it is broken down. Okay. And so that gives us a clue of the units. It's fed through a drying chamber where 98% of the water is removed. So this is an important part of this question or this problem. And 98% of the water is removed. So again, it's a separation problem. So we say for these non-reactive balance problems, for the majority of the problems, they are separation of some sort. And separation is very important in metals refining, obviously, because we're separating metal we want from ore. And we'll see examples later of hematite. So we want to separate iron from Fe2O3, which is hematite. The other iron ore is magnetite, Fe3O4. I digress a little bit. Let me get back to this problem. So now we have two flow streams leave the drying chamber, dried gas and a stream of liquid water. And this is interesting. It's liquid. So there's some things we don't know that we would need to know to figure out this stream. The volumetric flow rate of the gas is fed to the chamber at 100 cubic meters per hour. All right, so now we have a volumetric flow rate. And so we've marked everything. I'll go ahead and highlight the composition. And I could have easily have said the balance N2, and that would have told you that the rest of the gas mixture is N2. And we see that in looking at metal alloys as well. They'll say, percentage chromium and the balance iron or something like that. So what's the first thing we want to do? The first thing we want to do is draw a flow chart. And you know what? I didn't read what we're actually looking for. So that's, before we get to the first thing, we should finish reading the problem, I think. And so A, what is the volumetric flow rate of the product gas? And B, what is the composition of the product gas? Okay, so these are kind of the two things we want to know. And so we want to know what the volumetric flow rate of the product gas is, and want to know what the composition is. And sometimes people ask what I mean by composition. Well, we have this input gas that's 25% O2, sorry, 25% CO2, 4% O2, 20% H2O, and 51% N2. But we want to know, after it's gone through the dryer, what the composition of the gas is. So to solve this problem, first we want to draw our flow chart. and typically just use a box. You can use other symbols if you want. And then we have some gas coming in, and we have a volumetric flow rate. And let's go ahead and write out the composition. This is 25% CO2, 4% O2, 20% H2O, and 51% N2. We have a liquid stream of water, and then we have this output gas, and the V is what? We don't know. We don't know what the volumetric flow rate is of that. Here we know the input volumetric flow rate, and it's 100 cubic meters per hour. And so this one's a little bit different than the other balance problems we've had. We can't really figure out this. And I'll tell you why. Oops. Excuse me. Oh, come on now. You can see my scattering of notes. I apologize. Sorry about that. So we can't figure this flow rate. And I don't want you to think you can't solve what we're asking for the problem. We actually can. And my tablet's is acting strange. So we can't figure this V, or this volumetric flow rate. And the reason we can't is we don't know the conditions. And by conditions, I mean temperature or pressure, okay? And if we figure that out, for an ideal gas at STP, okay, and this composition is going to be the same regardless, you know, we probably could. We could figure this V out. Okay, all right, so we have our flow chart, we have our composition drawn here. All it's asking for is this volumetric flow rate. And in the other problems, we would, if this was like the other problems, we would have had to have figured out this volumetric flow rate somehow. But we know that 98% of the water is removed, okay? And that's very interesting. And we have a input volumetric flow rate. So this here is our basis. That ends up being our basis, that 100 cubic meters per hour. And so we have a basis of 100 cubic meters. And so that means that we can rewrite this composition and then we can kind of take a secondary basis and just say 1 hour. And the only reason I'm even bothering writing this is because we don't have to write the units. We don't have to write per hour for everything. So we can rewrite this composition. So I'm going to redraw it. You don't have to redraw it, but I'm just kind of doing it because I got a little messy up here. And that's going to be our output. So our input, it's 100 meters cubed per hour. So now we can say we have 25 and 4 cubic meters and 20 cubic meters and 51 cubic meters of nitrogen. And you're lagging on me, machine. Okay. And it told us that we've gotten rid of 98% of the water is removed. Okay. And so 98% of this ends up here. Okay, so it's kind of a mini water balance, but 0.98, and I can't say this is the volumetric flow rate of this stream because this is a gas in this output stream. They told us it's a liquid, but we know how much left and ends up going into this stream here. So 0.98 cubic meters, oops, sorry, 0.98 times 20, and I should have started off water removed. Water removed. So 0.98 times 20 cubic meters. And let me go ahead and just write it out, or calculate it out. Is 19.6. So 19.6 is removed. So the water that goes to here ends up being 20 minus 19.6 equals 0.4 cubic meters of H2O. Okay, and so all of this, the rest of this, all of it goes to the other side. Okay, so input totally equals output from here to here. Okay, this 98% that was removed, this 19.6, let me kind of color code it. This 19.6 is going out. We don't quite know what the volume is because we went from a gas to a liquid. It's kind of hard to solve for this because we don't know temperature and pressure. So we could probably figure out moles or something and then figure out this stream. But this stream, we don't know it. All we know is that at one point in time, 19.6 cubic meters of a gas was taken off into a liquid somehow. But we know that this 0.4 cubic meters of water is still in gaseous form. And we know that all the other gas goes through. Okay, so 0.4 cubic meters of H2O. And what this is going to give us is this is actually going to give us our V out. So V out equals 0.4 cubic meters of H2O plus 25 cubic meters of CO2 plus 4 cubic meters of oxygen plus, oops, that's our H2O, we don't need that, plus our 51 meters of nitrogen, 51 cubic meters of nitrogen. And so it's going to be less than 100 cubic meters. It's going to be less than our input because we took out some H2O. So 0.4 plus 25 plus 4 plus 51 equals 80.4. And so that means V out cubic meters per hour. Okay? So the volumetric flow rate out is actually less than the volumetric flow rate coming in for the gas. Okay? The volume of this liquid water is a little bit tricky because it went from a gas to a liquid, so the volume is going to be different. Okay? So I can't really say what the actual volume of the liquid is. So let's go to part B, and that wasn't even the answer of the question anyway. So we want to know what the volumetric flow rate of the product gas is. We know what it is. Part B is the composition. What's the composition? Composition. And that's basically the volume fraction of the constituents. And if you remember when we were doing mass and mole fraction, Vx equals Vi over V total. So let's just go by gas. We can even follow the same order. We can do CO2, O2, H2O, N2. So for CO2, it's VCO2 equals 25 over 80.4. And I can keep the units, they're going to cancel anyway. And so I got roughly 31 or 0.31. The second one's VO2, and it was 4. If you look, 4 meters cubed. Come on, don't lag. Screen's lagging. There you go. And so 4 over 80.4 is, I'm going to round up, 0.05. And the next one is V H2O, which is going to be very small because we dried it. It was 0.4, wasn't it? Come on, it's lagging, it's killing me. Okay, 0.4 divided by 80.4. And I got 0.00, I'm going to round up. 0.005. And the last one is N2, I believe. Yes. And let's work that out. I didn't put the meters cubed here, I'm sorry. All right. And that's 0.63. So you want percentage. If you want percentage, so this is 31% CO2. This is 5% O2. This is 0.5% H2O. And this is 63% N2. And so to check this answer, this should all equal 100, or pretty close, rounding all that, you know. I'm probably off by a little bit, obviously, but pretty close. So I got 99.5. Rounded wrong somewhere. So it should be pretty close to 100. And yeah, a little bit rounding, but this is pretty much the composition. Okay, I may have made a little rounding error, but this is how you do it. Pay attention to the technique. I've been a little off on some of these answers by a few tenths of a number, but really order of magnitude is the big one there. And so we've answered the question. We figured out how we figured out the output volumetric flow rate, and we figured out the composition. To figure this out, we'd have to know how many actual moles this was, I believe, and because we don't know if it's at STP. So if it's at STP, the mole fraction equals the volume fraction, and but we don't know if this is STP. Okay, so we can't really answer this question, how much volume of liquid water. If someone asked, it would be a little hard. We'd have to know the temperature and pressure conditions. But anyway, this is how you would do one. Here's an example of volumetric flow rate. A little bit different. We didn't really have to do much algebra, but it's another example of a mass balance problem, this time using volumetric flow rate. Oh my! It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.